Okay, so this little video is about longitudinal and transverse waves. So these are two types of travelling wave, and we can use the word longitudinal and transverse to describe its motion. So for a transverse wave, okay, if we're thinking that the wave direction is moving in this way, okay, so the energy being propagated is moving in this direction. The oscillation is perpendicular to the direction of the energy that is being transferred. Okay, so we always say that the oscillation is perpendicular to the wave direction, energy direction. It doesn't matter which way round that you say this, so the wave direction or the energy. Okay, whereas a longitudinal wave, if we look at this, again, the wave displacement's going here. Sorry about my terrible diagram, but this is almost like when we're going along, we have these series where they get bunched up and then spread out and then pushed up and spread out and pushed up, spread out as it moves along. So it's almost like the slinky that you've seen in class. So in this case, the oscillation is in the same direction. So we say that it's parallel. Okay, so for longitudinal, okay, we say that the oscillation is parallel, okay, to the wave or energy direction. Okay, now with the longitudinal diagram, we have those areas where we're talking about them being really bunched up and really spread out. Okay, the areas that are bunched up, we call those a compression. And the areas where they're really spread out, we call those a rarefaction. Apologies my accent for that, rarefaction. Okay, so there's areas where they're really pushed close together and then areas where they're really spreading out. Okay, compression is easy because we're compressing it, and rarefaction when we're spreading it out. Now most people are really okay with transverse waves and labelling the wave, but students often get really confused when we start trying to use this sort of shape of wave to represent a longitudinal wave. So I've got down here, and this is a longitudinal wave, okay, being represented with a displacement versus distance graph. Okay, so you can see I'm getting that typical wave shape to kind of be shown here. So what I'm going to ask you guys to do is just have a little look at the bottom. Okay, and this is what's kind of talking about in terms of like my blue particles, and the blue particles are not being displaced, so they are at zero. Okay, so they are still in their mean equilibrium position. Okay, so if I look then to the particles to the right and to the left of it, I need to look at what their displacements are. So if we take, we start from here. If we take this particle on this side, let's say we're taking it at this point here, it has been displaced in the positive direction. We've got our positive displacement. So I'm saying my positive displacement was moving to the right because my longitudinal wave was moving to the right. So in this case, it's moved to the right. So the particle is moving towards this little blue one from its mean position. If I then go to the next side of this particle, so the particle to the left, we see that it's got a negative displacement. So this means that it's moving backwards. So we can see that both of these particles are moving towards the blue one from the center. Okay, so that means that this here must be a compression, okay, at this point, all right? If I then go across to my next mean point and I look at the particles to the left of the blue one and its mean equilibrium position, the one that's not moving, I can see they've got a negative displacement, which means they're moving away from the mean particle, okay, which means that they are moving in the left direction because they're going in the negative. Okay, so I can see that it's moving away from it there. If I look to the right of the particle, we can see they've got a positive displacement, so they are also moving to the right. So again, they are moving in this direction. So you can see from this blue particle, both of them are moving away, meaning that this one is a rarefaction. Okay, again, just to repeat it back on this side, we can see this one here must be a compression. Particles to the left are positive, so they're moving to the right, they're moving towards it. Okay, particles to the right of it are moving negatively, so they're moving to the left, so they're getting closer again. So we have another compression, and I can see that moving along there. The last thing I just realised I forgot to mention before is the examples of transverse waves. So transverse waves, we can have all the electromagnetic waves. Okay, so radio waves, sorry, I've just completely had a blank there. Microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. Okay, we can also talk about, I'm really sorry, that's my cat trying to eat paper. We also have waves like on the top of water, so those will also be like at the top. So we have some sort of water, okay, at the top specifically. And the other one is a type of seismic wave, okay, so known as S waves. There are also examples of transverse waves. Longitudinal, okay, any type of sound wave. So we have also the infra sound and ultra sound. And also with water, not the water at the top, but the one really deep down, that also moves by longitudinal. So I can also say water below. And again, a type of seismic wave, so waves that are used within Earth that create earthquakes, not the S waves, but actually a type of wave called a P wave. So that's another type of seismic wave. And that's just a little recap on transverse and longitudinal. They like asking for the description, and they like sometimes doing this description with the graph there, getting you to tell me whether it's a compression or a rarefaction. The other one is that sometimes they might have a little multiple choice on identify which is the transverse wave or identify which is the longitudinal. Just be careful, ultrasound, sometimes they call that ultrasonic as well. And that's about it, guys.